we're going to be taking notes on the first part of Unit 3, which is LT1, electron arrangement, which correlates with Chapter 5 in your textbook. You can use this notes guide to help you take notes, or you can write your own notes on a piece of paper if you prefer. At the end, we will be using this document to just review the vocabulary. So you will need both of these things. Yesterday in our glow-in-the-dark lab, we started our learning on electron arrangement and motion in a fun way, hopefully, for you. Just like these fireworks are giving off different colors of light, the things that glowed in the back, some of them glowed different colors. Some of the chemical glowed if it was struck by a certain type of laser. Any type of light that you can think of, burning a piece of wood and it burning different colors, if you've ever seen green flecks or red flecks or orange or yellow in a piece of wood that you've thrown in the fire, all of that, all of those different sources of light have to do with electron movement. Just like a light works, if you've ever heard of a filament blowing, so the electricity can't flow through that wire and create that light, it's the same idea. Electrons are moving. So that is what creates light for us, and in different colors as well, is electron movement. So that is how electrons and light are related, and we're going to talk about the different colors that can be seen as well. This is a video link. If we don't have time to watch it in class, this PowerPoint will be on the web page and you can watch it. It's a howstuffworks.com video, I believe, and it's about how fireworks work, so it's pretty cool. Okay, so up to this point, what do we know about electron arrangement? It's not very much. We went from the plum pudding model that Thomson said, that all electrons are just randomly scattered throughout the atom, to Rutherford's idea of a nuclear model. And that means that there is a nucleus where the positive protons are and the majority of the mass is found, which was a great discovery using that gold foil experiment. The only thing he said about an electron is that they're outside the nucleus flying in empty space. So he didn't even know about these rings. If you see these things right here, he just knew they were outside the nucleus. The problems, it did not explain electron arrangement, why electrons aren't pulled into the nucleus since they're negative and the nucleus is positive, or the reactivity or properties of atoms. Now, the reactivity and property is directly related to electron arrangement, so it makes sense. If he didn't know about electron arrangement, he couldn't predict the properties that atoms would have, or set up a periodic table or anything like that. Now, you have to first understand what EM radiation is and the characteristics of waves in order to understand how electrons relate. So EM stands for electromagnetic radiation. It has characteristics of waves. So the first thing I want you to look at is one complete cycle. It is from one point to another similar point. So you could have one wavelength could be crest to crest. You could have one wavelength being trough to trough. You could have one wavelength being one point to another similar point. So you do need to look at what a wavelength consists of. The frequency is the number of waves passing a point in a given amount of time. And that's going to be measured in something called a hertz. So I want to go ahead right here and write down the unit for frequency is in hertz. And that is the number of waves that pass a point in how many seconds typically. So if it's one wave per second, then that would be 1 hertz. That's our unit that we're going to talk about with frequency. All right, next thing, the relationship between wavelength and frequency of EM waves. How is energy related? So let's go ahead and label our waves here so that you can see how they're measured. And there is a typo or a picture problem here, so we're going to fix it. So here is one point of a wave, and here is the same point. So I went from trough to trough. That was one wave per second, which equaled 1 hertz. Here is just past the trough. Just past the trough, there's 1, and then here's my half. So that's 1.5 waves per second. Now let's count this one. Here's my trough, trough. There's 1, 2, 3 and a half. So that is incorrect. That is 3.5 hertz or waves per second. So the longer the wavelength, the lower the frequency. The shorter the wavelength, the higher the frequency. And energy is directly related to frequency. These have a direct relationship. So as frequency increases, so does the energy. Wavelength and energy have an indirect or an inverse relationship. So this would be a direct, and these would be an indirect or an inverse. So as your wavelength gets longer, your energy goes down. Alright, so there are different types of EM radiation or electromagnetic radiation. Now, what is electromagnetic radiation? They are natural waves created by electric and magnetic fields moving at right angles to each other. It's a natural phenomenon on Earth that we have electromagnetic radiation. So all of these waves are created by the same thing. What's different about them is the wavelength, long wavelengths on the radio ends, short wavelengths on the gamma ray or wave ends, and then the frequency, high frequency, low frequency. So that would correlate with energy, high energy, low energy. Now specifically, we are going to be staying in this realm right here, in the visible end, or the visible, I guess it's in the middle, visible part of the spectrum. And specifically, I need for you all to know Roy G. Biv, which puts the colors in order of the rainbow. Red being less energy, lower frequency and longer wavelength, and violet being your higher frequency, shorter wavelength. So during this entire unit, we're going to be talking about electron movement in light, and specifically referring to how the visible light spectrum correlates with it. All right, another component of a wave is its amplitude. And a definition for amplitude is just the distance of the wave off of the wave motion. So if your wave motion would be this line right here, then the distance off of it is here, and that's called its amplitude. But what does it mean? What does amplitude tell you about a wave? It's going to tell you the intensity of the wave. So how quiet or loud is the sound, how high or low is the pitch, how bright or dull is the light. So the amplitude will tell you the intensity of that wave. Alright, so there's a wave model of light. Light is part of the visible spectrum, and it is an electromagnetic wave. So why did the idea need to be revised? There were two things that made it have to be revised. One is kind of complex. It's called the photon effect. And it's where when metals are emitting electrons when they're struck by certain types of light. When metals are struck by a light with enough energy, electrons can move off of those metals, and the wave model of light didn't explain why that occurred. The other thing that's a little more concrete, it's a little easier to understand, is why different metals glowed different colors when they were heated. You can think about it in terms of when you burn things. You throw a piece of wood in the fire and it may burn a green shade, or it may have like red flecks if you're lucky, or it might just burn a little bit yellower than maybe other pieces of wood. Or if you put metals into flames and they burn different colors, it didn't explain why different colors came off of heated objects. So Planck came up with an idea called a quantum. And for quantum, I want you to think quantity or amount, because that's what it is. Planck said matter doesn't gain a continuous amount of energy. It's not like going up a ramp where there's no finite amount of how much you're moving up. You're just moving up on a continuum. Instead, a matter gains an amount of energy that can be measured. It's kind of like going up a stair. There's a certain amount there, there's a certain amount there, there's a certain amount there, and that's how matter gains energy, by gaining a certain amount. Now, some matter can gain small amounts, like small stairs, like at a stadium, and some matter can gain a lot of energy, like an RV step, a lot more, but it's a certain amount. and the colors emitted from the object when heated is directly related to that quantum. So that quantum is your idea of amount or quantity. Now let's take a moment and think, well, what is light? Is it a wave or is it a particle? Well, I want you to look at this picture for a couple of minutes and say, all right, well, what would this ball represent? That would represent the photons or the particles that make up light. But the squiggly line here is showing you how the light moves. Those photons are particles that move like waves. So they do have a dual nature, where they're made of particles but move like waves, like EM waves. Now, why do we see colors from neon signs? And this is going back to why do we see different colors when we burn different metals? And why do we see different colors when we throw different kinds of wood in fires? It's because they have different matter made up in that wood as they're decomposing. And so this is a good picture, but I'm also going to draw one here with you. All right, I want you to first draw the nucleus of an atom, and I want you to draw the circular patterns around the nucleus, and we're going to label these as energy levels. And mine are kind of close together, but energy levels. There are 7 total. The biggest atoms would have 7 total. When an electron starts, it is going to start in what's called its ground state. So the beginning part, wherever it is, let me switch colors for you, is called the ground state, and that is where the electron is stable. Okay, so in our lab, before you shined, before the stars would glow, we had to turn the lights on so that they absorbed energy from the lights, and so we hit them with an energy source. So your matter would have to be hit with energy, and that could be in the form of light, that could be in the form of fire, that could be in the form of a laser beam. It's going to be hit with energy. Okay, when that electron is hit with energy, it jumps out to what's called the excited state. It has absorbed energy and it jumps out, and now it's in the excited state, but it is unstable out here. When the electron then returns back to ground state where it came from, it's going to emit light in the form of photons in specific colors, specific frequencies. So it didn't emit the colors when it jumped out to excited state. It emitted the colors as it fell back and released that energy that it had absorbed. So the releasing is where you see the light. So you go back to the screen that says, what do you think the color depends on? And in this example, neon is emitting red and argon is emitting blue. And so if you're thinking, well, it has to go along with Roy G. Biv, and the colors associated, neon absorbed a lower quantum of energy, where argon absorbed a higher quantum of energy and released a higher frequency color. Here it is all written out for you in words. I'm going to have to go through this kind of quickly because I'm running out of time. But atoms hit with energy, the electrons are excited, they fall back to the ground state, giving off light. The color depends on quantum. Higher quantum would be on our Biv end of Roy G. Biv. The lower quantum, the atoms that gain a lower quantum would be on our Roy end of the spectrum, red, orange, and yellow. Okay, so what is atomic emission spectrum? Our eyes see a continuous color, like we see orange, or we see yellow, or we see red. We don't see all of the frequencies that make up that color. We see one continuous color. A spectroscope can break down that continuous color into discrete bands of different frequencies. So when you see sodium burn in our lab, it'll just look orange, but it actually has greens in the 500 nanometer region. Calcium, you'll say it's just orange as well. We'll use that one too. But look at all the colors that make up just the plain orange that we see with our naked eye. So this is the atom's fingerprint. It is specific for each atom, and it's like its identity. And you have to have a machine to do it, but it does break down all of the continuous color into the set of frequencies specific to each different kind of matter. All right, I want you to practice using your vocabulary, and then you need to hit pause, because here is the key. I do want you to check your answers, and let us know if you have any questions.